We now start chapter 3 module 5 and we will be discussing determinants of square matrices. We have learned that rank of a matrix is an extremely important number associated to a matrix, and that can be calculated with the help of elementary row operations on the matrix. We have seen that we can achieve something called the row reduced echelon form of a matrix, and then the number of non-zero rows in the row reduced echelon form gives the rank of the matrix. And now we are going to introduce another very important number associated to a matrix called the determinant. But calculating the determinant is perhaps more difficult compared to calculation of rank. But once again, we will be able to derive extremely important properties of a matrix using determinant. And what is important is that determinant, which will be defined as a function from the set of matrices to the base field, is in fact a polynomial function. Let F denote a field. Let A denote a 2 cross 2 matrix over the field F with entries A, B, C, D. The determinant of A is defined to be the scalar AD minus BC, and we denote it by det A. For example, if you look at the matrix A given by minus 1, 1 in the first row, 1 minus 1 in the second row, then by this definition determinant of A is 0. Now, it is a easy verification that for a fixed vector A comma B in F2, the functions phi1 and phi2 defined from F2 to F and given by phi1 of xy is equal to determinant of ABXY, that is AY minus BX, and phi2 of xy is equal to determinant of XYAB, that is BX minus AY, are both linear functions. Theorem: let A be a 2 cross 2 matrix with entries from the field F, then determinant of A is not 0 if and only if A is invertible. Moreover, if A is invertible, then the inverse of A is given by A inverse is equal to 1 over det A multiplied by this 2 cross 2 matrix, whose first row is A22, A12 and the second row is minus A21, A11. Suppose that det A is not 0, then the definition of 1 by det A multiplied by A22, A12 minus A21, A11, which we call P, this makes sense. And if we multiply the matrices A and P from left and right, then we get AP is equal to PA is equal to I2, that is the 2 cross 2 identity matrix. Therefore, P is the inverse of the matrix A. Conversely, if A has an inverse, then we know that rank of the matrix A is the full rank, that is 2. Therefore, either A11 is not 0 or A21 is not 0. If A11 is not 0, then we apply the elementary row operation on A and reduce it to the form where the first row is A11, A12 and the second row is 0 and then A22 minus A12, A21 by A11. Therefore, A22 minus A12 A21 by A11 is not 0, because we know that rank of A is 2. Therefore, we cannot have one 0 row for a 2 cross 2 matrix. This therefore proves that determinant of A, which is defined to be A11 A22 minus A12 A21, that is a non-zero element in the base field F. This proves the theorem. Let us now define what is called an orientation of a basis. So, let B denote this set containing V1, V2, which is an ordered basis. Suppose that V1 is this row A11, A12 transpose, that means V1 is actually in the column form, and V2 is A21, A22 transpose. Since we know that V1, V2 form a basis, therefore they are linearly independent, and therefore the determinant of this 2 cross 2 matrix A11, A12, A21, A22, which is in our notation determinant of V1 transpose V2 transpose, and that is non-zero. Now, we define the orientation of the basis B to be the number denoted by OB, and that is given by this quotient determinant of the matrix A11, A12, A21, A22 divided by modulus of the determinant of A11, A12, A21, A22. In other words, it is determinant of V1 transpose V2 transpose over modulus of determinant of V1 transpose V2 transpose. And we assume that the base field is the field of real numbers, and therefore, this is plus or minus 1. And if this set consisting of these two vectors V1, V2 is linearly dependent, then we define the orientation of this set V1, V2 to be 1. Definition: we call an ordered basis B or a coordinate system right-handed if orientation of the basis is 1. For example, the orientation of the standard basis E1, E2 of R2 is 1, and the orientation of this basis E1 minus E2 is minus 1. Therefore, whether the system is right-handed or not would very much depend on the basis that we choose to work with. Let U and V be vectors in R2. Let us see these vectors as rays emanating from the origin. And then the parallelogram defined by V1, V2 is denoted by this box V1, V2, which is the parallelogram having V1 and V2 as adjacent sides. Let us denote the area of the parallelogram, this box V1, V2, as A of box V1, V2. If V1 and V2 are linearly dependent, then the parallelogram is in fact a line, and we call it degenerate, and in that case the area is 0. Let us now see what happens if V1 and V2 are linearly independent. That means it is non-degenerate parallelogram. Theorem: suppose that V1 is the vector A11, A12 and V2 is the vector A21, A22. We actually write them in column form. So, they are vectors in R2, and then we claim that the area of the parallelogram box V1 comma V2 is modulus of the determinant of this 2 cross 2 matrix A11, A12, A21, A22, or in other words it is modulus of determinant of V1 transpose, V2 transpose. Our proof follows from the fact that A of V1, V2 is the orientation of V1, V2 multiplied by the determinant of this matrix A11, A12, A21, A22, or equivalently the orientation of V1, V2 multiplied by A V1, V2, that is the area, is equal to determinant of this matrix A11, A12, A21, A22. You can see that they are indeed equivalent, because if we multiply by this orientation on both sides, then that being plus or minus 1, the square becomes 1, and therefore one expression implies the other and vice versa. How to prove this statement? We define the function delta from M2R to R. M2R stands for the collection of 2 cross 2 matrices with real entries, you have seen that before, and delta is defined as orientation of V1, V2 multiplied by the area of the parallelogram V1, V2 box. And then it follows that this function delta is nothing but the determinant of this 2 cross 2 matrix A11, A12, A21, A22. But how to show that? We will be able to prove that delta is nothing but the determinant function on M2R if it satisfies the following properties: that delta is linear in each row of the matrix when the other row is fixed. In other words, the function is bilinear from M2R to R, or as a function from R2 cross R2 to R, and if the rows are identical of a matrix A, then delta of A is 0, and delta of I2 is 1. I2 stands for the 2 cross 2 identity matrix. We will postpone the proof because we will see a generalized version of this characterization of determinant after some more preparation. We have defined determinant for 2 cross 2 matrices over a field F, and we have proved that the matrix A is invertible if and only if determinant is not 0. Earlier we had seen that invertibility of a matrix can be decided by the rank of the matrix, and now we have used rank to prove that theorem, that determinant non-zero if and only if A is invertible. So, we have already seen the importance of the determinant function, although for 2 cross 2 matrices. Also, for the vector space R2, we have seen that determinant can be realized as area of a parallelogram up to a sign, and we have introduced a very important concept of orientation of a basis, which becomes extremely important and useful when we want to do some geometry. And now it is time to extend our definition of determinant and define determinants for matrices of order n. Let us see. Let A be an n cross n matrix over the field F. If n is 1, then A is this 1 cross 1 matrix given by A11, and we define determinant of A11 is equal to A11. Now for n greater than or equal to 2, determinant of A is defined as summation j equal to 1 to n minus 1 raised to 1 plus j A 1j multiplied by determinant of capital A 1j tilde, and this is a scalar in the field F, where this capital A 1j tilde denotes the submatrix obtained after deleting the first row and the jth column of A. In that expression, the small a ij's are entries of the matrix, and we have just now defined this capital A 1j tildes, which are the submatrices obtained from A. Now, capital A ij tilde denotes the submatrix obtained after deleting the ith row and the jth column of A. And these scalars, which were denoted by Cij, given by minus 1 raised to I plus j, determinant of ij tilde, they are called the cofactors of the ijth entry Aij of the matrix A. Therefore, if we use these scalarsCij's, then that above expression for determinant can be rewritten as C11A11 plus C12A12 etc. up to C1n A1n. We can therefore see that determinant is a map from MNF to F, defined as determinant of A is equal to summation j equal to 1 to n minus 1 raised to 1 plus j small letter a 1j times determinant of capital letter A 1j tilde, and that is a scalar belonging to the base field F, and this is defined for every n cross n matrix A over F. This definition of determinant is called the Laplace expansion or the cofactor expansion along the first row. And if we identify the set of all n cross n matrices over F with the set F raised to n square, that means the Cartesian product of the field F n square times, then determinant can be seen as a map from Fn square to F. Proposition: determinant of In is 1. The determinant of a diagonal matrix is the product of its diagonal entries. The determinant of an upper triangular matrix is the product of its diagonal entries. And finally, determinant is a polynomial map from Fn square to F. Each one is easy to prove, and the main thing to use is induction on N. Definition: let A be an n cross n matrix over F, ijth entry of A is denoted by Aij. Let Ri denote the ith row of A, that is given by this n tuple Ai1, Ai2 and so on Ain. Then modulus of determinant of A is the n-dimensional volume of the parallelopipe having the vectors R1, R2 etc. up to Rn as adjacent sides. So, once again we see a concrete geometric realization of the determinant up to a sign, like what we have seen for n equal to 2, that represented the area of a parallelogram, and here this is the generalized version. A list of very important properties for the determinant function. Suppose that A is an n cross n matrix over F, then the following properties hold good for the function det. Det is the short form we use for the determinant function. Det is a linear function in each row when the other n minus 1 rows are kept fixed. 2. If one row of A is the 0 row, then det A is 0. 3. Det can be evaluated by cofactor expansion along any row, that is det of A is equal to summation j is equal to 1 to n minus 1 raised to I plus j Aij multiplied by determinant capital A I j tilde. So, you can see that this expression is the Laplace expansion or the cofactor expansion along the ith row. Our definition was with respect to the first row, but now it can be proved that the same det can be evaluated as a cofactor expansion with respect to any one of the n rows, gives the same result. 4. If two rows of a matrix A are identical, then det A is 0. 5. If the matrix B is formed by interchanging any two rows of A, then det B is equal to minus det A. And 6. If the matrix B is formed by adding a multiple of a row of A to another row of A, then det B is the same as det A. So, what is interesting here is that the last two statements, that is statement 5 and statement 6, are talking about the value of the determinant when we apply elementary row operations on a matrix A. So, on one case we see that the determinant changes sign, and in the other case it remains unchanged. But here what should be noted is that this changing sign, or rather getting minus det A, will make sense only if the characteristic of f is not 2. So, to understand it better, we can assume that characteristic of f is 0, so that minus 1 and 1 are different, and then we can indeed say that by interchanging two rows, det changes sign. Proposition: if A is an n cross n matrix over the field F, and if rank of A is less than n, then det A is 0. If the rank of A is less than n, then the rows of A are linearly dependent. That means rank is not the full rank, and therefore it cannot happen that all the rows are linearly independent. Hence, there exists a row which is a linear combination of the other rows, and then we can use properties 1 and 4 from that list and obtain that determinant of A is 0. We have learned the definition of determinant through cofactor expansion, and we have also seen a list of properties. These properties are not very difficult to prove. They can be verified using the definition. And now what we aim to understand is that what is a deeper characterization of the determinant function. We will see that these properties like separately linear with respect to each row, or the value of the identity matrix is 1, interchanging rows introduces a negative sign, etc., will indeed give us a characterization. And this will also settle the question we raised when we were discussing area of a parallelogram. Remember, we defined a function delta from M2R to R, and we had to check that it actually gives the determinant. After we understand the characterization of this determinant function, then that question will automatically be settled.